All right, so today we're taking a deep dive into a pretty fascinating area of mathematics.
Oh, yeah, definitely fascinating.
Bessel functions.
Yeah.
Now, these guys pop up pretty much everywhere you look, especially when you've got systems with, rotational symmetry.
Absolutely.
But here's the thing, integrating them, especially when they get all, highly oscillatory,
Yeah.
it could be a real headache.
Oh, it's a nightmare for a lot of traditional methods, right? You end up needing to take these tiny little steps in the integration, which just chews up computational time like you wouldn't believe.
Yeah, exactly. So today we're going to be exploring a new tool that might just be the answer to our prayers, at least when it comes to these Bessel integrants.
Yeah, I'm excited about this one.
It's called pylevin.
Okay.
And it's a Python package specifically designed to make these calculations much smoother, much more efficient.
Really? So it's Python-based?
Yeah,
Okay, that's already a good sign. I mean, Python's so widely used, it makes it super accessible.
exactly. And it's not just for single Bessel functions either. It can handle integrals with up to 3 of them at once.
Oh, wow, that's a big deal.
Yeah.
Because a lot of the existing solutions out there are really tailored for those single Bessel function cases.
Right, exactly. So pylevin really fills a gap, and it does it in a way that's both, flexible and efficient.
So it's kind of like a one-stop shop for all your Bessel integration needs.
Exactly, yeah. So before we jump into the nuts and bolts of how it works, let's take a step back and talk about why these Bessel integrals are so tricky in the first place.
Right, yeah, I mean, we've been integrating functions for centuries. What makes Bessel functions so special in this regard?
Yeah, well, it all comes down to those oscillations.
Right, the oscillations.
That's really the heart of the problem.
Yeah, you can picture it like trying to measure the area under a curve that's constantly zigzagging up and down.
Yeah,
And those traditional methods like quadrature, they kind of struggle to keep up.
they just can't capture all those twists and turns without taking like a ridiculous number of steps.
It's like trying to measure the coastline of Britain with a ruler.
Oh, yeah, I like that, all those little inlets and bays.
Yeah, it makes it way longer than you'd expect.
So that's where the ingenuity of pylevin comes in.
Oh, okay, so pylevin has a different approach.
It does. I'm curious to hear about that.
Instead of kind of fighting those oscillations head on, it uses this clever technique called Levin's method, and it basically sidesteps them.
Oh, really? So it's kind of like a judo move, using the oscillation's energy against them.
Exactly, yeah. So I'm kind of curious to unpack this Levin's method a little bit.
Yeah, me too.
Can you give us a breakdown? How does it work? How does it, turn these wiggly integrals into something we can actually compute efficiently?
Okay, so imagine you're dealing with a function that has like 2 parts to it.
You've got a smooth, well-behaved part, and then you've got this other part that's causing all the trouble with the oscillations, like our Bessel functions.
Right.
And Levin's method essentially says, okay, let's focus on those oscillations, let's kind of isolate them and figure out a way to describe them separately.
So it's like identifying the troublemaker in a classroom and giving them a special assignment
Exactly.
to keep them occupied.
Yeah, that's a good analogy.
So what does it do with those troublesome oscillations then?
So what Levin's method does is it represents those oscillations as a vector, and this vector satisfies a particular differential equation.
Okay, hold on a second. A vector, like an arrow pointing in a certain direction.
Exactly, yeah.
And a differential equation. Now things are getting a little bit abstract here.
I know, but bear with me, it'll make sense.
Okay.
So this vector, its direction is determined by those Bessel functions, right?
Okay.
And the way it changes as we move along our integration path, that's described by the differential equation.
Right, so it's like saying, hey, oscillations, we know you're going to wiggle around, but we've got this mathematical rule book that tells us exactly how you're going to do it.
That's a great way to put it.
Okay, so we've got these Bessel oscillations. They're tamed. They're described by a differential equation.
Right.
But how does that actually help us solve the integral? I mean, we haven't actually integrated anything yet, have we?
Right. That's the key question, isn't it? So this is where the real magic happens.
All right, lay it on me.
Levin's method connects this differential equation to our original integral through another vector and a set of strategic points.
Okay.
These points are called collocation points.
Collocation points up.
And they're like checkpoints along our integration path.
Right.
And by enforcing a particular relationship between our vectors and the integrand at these points, we end up with a system of linear equations.
Ah, linear equations. Now we're talking something we can actually solve.
Exactly. Much easier than trying to wrestle with those Bessel integrals directly.
So it's like translating a really difficult language into something that we're much more familiar with.
Yeah, that's a good analogy.
Okay, so pylevin takes this Levin's method and runs with it.
It does.
But what makes its implementation stand out? What makes it, special compared to other things that are out there?
Well, for one thing, it's incredibly user-friendly.
Okay.
It's written in Python, which is a language that, a lot of scientists and engineers are already familiar with.
Yeah, exactly.
And it has a very clean, well-documented interface, so you don't have to be a coding wizard to use it.
So it's like the easy to assemble furniture of Bessel integration.
Exactly. You don't need like a PhD in computer science to put it together.
Yeah, and it's not just easy to use, it's also remarkably efficient, right?
Oh, yeah. The core code is actually written in C++O, which is known for its speed,
Right.
and it leverages parallel processing to really crank through those calculations.
So it's like having a team of super fast calculators all working on the problem simultaneously.
Exactly. Each one tackling a different part of the integral.
Yeah, no wonder it can handle those complex integrals with multiple Bessel functions so effectively.
And there's another trick up its sleeve,
Oh, okay, what's that?
It can actually reuse pre-computed quantities.
Oh, that's interesting.
Yeah, and this is particularly useful in applications where you're repeatedly calculating similar integrals with only slight variations.
Okay, yeah, I can see that.
Like, think about MCMC simulations, where
Right.
you're constantly tweaking parameters and then recalculating integrals.
So it's like having a master chef who've prepped all the ingredients in advance.
Exactly.
They can just whip up different dishes really quickly by just swapping out a few key components.
That's a great analogy.
So pylevin can store those time-consuming calculations that involve the Bessel functions,
Right.
and then quickly adapt them to different scenarios.
Exactly. It saves a ton of time and computational resources, especially for those large-scale simulations.
Well, I'm already impressed, but before we get too carried away, let's see how pylevin actually performs in the real world.
Yeah, let's see how it stacks up.
Now, the paper mentions some benchmarking tests where they compare pylevin to some of the heavy hitters in the field.
Oh, yeah, they put it through its paces.
So first up, they tested it on the classic Hankel transformation,
Right.
and they used a package aptly named Hankel.
Makes sense.
So it's like a head-to-head match between pylevin, this generalist,
Right.
and Hankel, the
The
specialist.
specialist, yeah.
How did that turn out?
Well, pylevin held its own remarkably well.
Really?
Yeah, it achieved comparable speed and accuracy to Hankel, even though Hankel is specifically designed for Hankel transformations.
That's impressive. So even when facing a specialist in their own domain, pylevin can keep up.
It can, yeah.
What other challenges did they throw at it?
Well, they moved on to a problem from cosmology, calculating the galaxy power spectrum monopole.
Okay.
This involves integrating a function with a single Bessel function,
Right?
and they compared pylevin to Hankel, a package that leverages FFT-log, which is another technique for Bessel integrals.
Okay, so another specialist, this time from the world of cosmology.
Yeah.
How did pylevin do against Hankel?
It was a close race.
Oh, really?
Yeah, Hankel was slightly faster in this particular scenario.
Okay.
But pylevin was right on its heels, so it shows its ability to compete even with algorithms tuned for specific applications.
So it's still a very strong contender.
Absolutely.
All right, so we've seen it go up against Hankel transformations. We've seen it go up against, the galaxy power spectrum monopole.
Right.
What else did they test it on?
Well, they also compared it to pythlog, a package that's specifically designed for FFT log transformations.
Right.
They used a particular test integral for this.
Okay.
And once again, pylevin matched pythlog in both speed and accuracy.
So it's like the Swiss Army knife of Bessel integration.
It really is. Yeah, it's got a tool for every situation.
It's got a tool for every situation.
Yeah.
But I'm guessing they didn't stop there, did they?
Of course not. They wanted to see how it would handle a really demanding task, calculating the angular power spectrum in the non-limber projection.
Okay, now this sounds interesting.
It is.
Non-limber projection.
Yeah, this involves not one but two Bessel functions.
Oh, wow.
And for this, they chose PyCCL as the opponent.
Okay, PyCCL. Now that's a name I haven't heard before.
It's a highly optimized cosmology code.
Okay.
And it uses a specialized FFT log implementation for this specific calculation.
So it's like bringing in a seasoned professional
Exactly.
who spent years honing their skills for this exact task.
Yeah, the ultimate test.
Okay, so how did pylevin measure up against this heavyweight champion?
It was a tough battle, but pylevin put up a good fight.
Okay.
So while PyCCL was faster,
Right.
because of its highly tuned nature, it's very specialized,
Right.
pylevin still delivered remarkably accurate results.
So even when facing a highly specialized opponent, it can still hold its own.
It can, yeah.
That's impressive.
And it actually highlights a key point, while these specialized tools can excel in certain situations,
Yeah.
pylevin's general approach allows it to perform well across a broader range of problems.
So it's a bit like the tortoise and the hare.
Yeah, I like that.
PyCCL might be faster on a particular track, but pylevin can handle a lot of different terrains.
Exactly. And there's another crucial aspect to consider as well.
Oh, okay. What's that?
So PyCCL's method relies on an assumption called separability,
Okay.
which means that the function you're integrating can be neatly split into separate parts.
Okay.
But in some cosmological models, this assumption might not actually hold true.
Right.
And that's where pylevin has an advantage,
Okay.
because its approach doesn't depend on this separability assumption.
So it's kind of like pylevin is that friend who's always prepared for anything,
Exactly.
whereas PyCCL is more of a specialist who might struggle when things go off script.
Yeah, that's a good way to put it.
All right, so we've talked a lot about pylevin's performance against these, these specialized tools.
Right.
But I think that the real test where it really flexes its muscles is when we're dealing with integrals involving multiple Bessel functions.
Oh, yeah, absolutely.
So how does it handle those multi-Bessel beasts?
That's where things get really interesting.
Okay, I'm ready.
Traditional methods, they really struggle with these kinds of integrals.
Yeah.
Imagine trying to track the movements of multiple jitterbugs on a dance floor. It's just chaos.
Yeah, I can only imagine the computational headaches.
It's a nightmare.
So how did pylevin do in this ultimate showdown?
It absolutely crushed the competition.
Really?
Yeah, they used 2 test integrals,
Okay.
one with 2 Bessel functions and another with 3.
Right.
And they compared pylevin to the standard adaptive quadrature method.
Okay, adaptive quadrature. Now that's like the workhorse of numerical integration, right?
It is, yeah, but it's just not designed for these highly oscillatory multi-Bessel integrals.
Right.
And the results showed that pylevin outperformed adaptive quadrature by orders of magnitude in speed,
Wow.
while achieving better accuracy and stability,
Okay.
especially when the arguments of those Bessel functions got large.
So it's safe to say that pylevin is the undisputed champion when it comes to these multi-Bessel integrals.
It really seems that way, yeah.
That's amazing.
It's a game changer for fields like cosmology, signal processing, optics.
Right, all those areas where these integrals pop up all the time.
Absolutely.
Well, I'm convinced pylevin sounds like a really, an incredibly valuable tool.
It is.
But before we wrap up this part of our deep dive, can you give us a little sneak peek into what we'll be exploring next?
Yeah, sure. So in the next part, we'll actually dive deeper into the mathematical nuts and bolts of Levin's method.
Okay, sounds good.
We'll unpack those equations we've been hinting at,
Right.
and really try to understand how this technique works its magic.
Sounds fascinating. I'm ready to geek out on some serious math.
And for our listeners, don't worry if you're not a math whiz, we'll break it down in a way that's clear and engaging, even if you haven't seen a differential equation since college.
That's right. We'll make sure everyone can follow along and appreciate the elegance and power of Levin's method.
Absolutely.
So stay tuned because things are about to get really interesting.
Yeah, they are.
Welcome back. So I'm still kind of reeling from that last segment. Pylevin really does seem like a game changer.
Oh, it is.
For these Bessel integrals, especially when you've got multiple Bessel functions involved.
Yeah, it's pretty remarkable.
But now I'm really curious to kind of get under the hood a little bit and understand how this Levin's method actually works, the magic behind it all.
Yeah, happy to dive into that. It's one thing to see the results, right?
Yeah.
But understanding the underlying math is where the real beauty lies.
Okay, so let's roll up our sleeves and get into those equations. But promise me you'll keep it accessible for those of us who haven't dealt with differential equations in a while.
Absolutely. No need to dust off those old textbooks. We'll walk through it step by step using intuition and analogy so everyone can follow along.
Okay, great. So where do we begin? What's the fundamental idea behind Levin's method?
Well, the starting point is recognizing that integrating these highly oscillatory functions directly is it's a recipe for disaster. It's like trying to navigate a maze, blindfolded,
Right.
messy, inefficient.
You're bound to bump into a few walls.
Exactly. So Levin's method offers a more elegant approach. It transforms the integration problem into a different kind of problem, solving a system of linear differential equations.
Okay, differential equations. Now, those sound a little intimidating.
I know, they have a bit of a reputation, but they're not as scary as they sound.
All right, well, demystify them for us a little bit then. What exactly are we talking about here?
Okay, so think of a differential equation as a mathematical rulebook. It describes how something changes over time or space.
Okay.
In our case, it describes how those pesky Bessel oscillations behave as we move along our integration path.
So it's like having a GPS for those oscillations, guiding you through all those twists and turns.
That's a great analogy, and just like a GPS helps us find the most efficient route, this differential equation helps us find a more efficient way to compute the integral.
Okay, I'm starting to see the light here, but how do we actually go from an integral to a differential equation? That seems like a pretty big leap.
It is a big leap, and that's where the ingenuity of Levin's method really shines through. So let's start by looking at the general form of the integral that pylevin tackles. It looks something like this.
Okay.
I1 K2 K3 equals BA dx fx, Ni equals 1 J(x), N equals 1, 2, 3.
Okay, I see. We've got our Bessel functions in there, represented by those JO case terms, along with that f of x, which I guess is our well-behaved function.
Exactly. That's the smooth part. But yeah, it still looks pretty intimidating, I'll grant you that.
It does. It does. So how do we break this down?
All right, so the key insight is to separate those rapidly oscillating Bessel functions from the rest of the integrand.
Okay.
We can think of it as having two parts, a smooth part represented by that fx,
Right.
and an oscillatory part, which are those Bessel functions.
So it's kind of like separating the wheat from the chaff, focusing on those troublemakers.
Exactly, we're isolating the source of the problem.
Okay.
And now Levin's method comes in and says, okay, let's represent those Bessel oscillations as a vector, call it W, that satisfies a specific differential equation.
A vector, so we're back to that arrow pointing in a particular direction.
Exactly,
Right.
and its direction is determined by those Bessel functions.
Okay.
And the differential equation, it describes how this vector changes as we move along the integration path.
So we're giving those oscillations a mathematical leash, controlling their movements.
Yeah, that's a good way to visualize it.
Okay, so what does this differential equation actually look like?
All right, so the specific form is crucial here. It looks like this. dw a of x ddx equals axx.
Okay, now we're getting into the nitty-gritty. Can you break that down for us a little bit? What's ax and what does dwx dx represent?
Sure, so dw(AHX), that's simply the derivative of our vector, w with respect to x, our integrational variable.
Okay.
It tells us how the vector changes as we move along the x-axis.
So it's like the speedometer for our oscillations, showing us their rate of change.
Exactly. And AX, that's a matrix, which you can think of as a grid of numbers.
Okay.
And it depends on X, and this matrix, it encodes the specific rules governing those oscillations determined by the Bessel functions and their arguments.
Okay, so we've bundled our Bessel functions into this vector W, which is controlled by this differential equation involving this matrix A of x.
Right.
But I'm still not seeing how this helps us solve the integral.
Right, so that's where the next clever step comes in, connecting this differential equation back to our original integral. And Levin's method does this through another vector, let's call it P.
All right, P, okay.
And a set of special points, those collocation points we mentioned earlier.
Right, those collocation points, like checkpoints along our integration path.
Exactly, strategic points where we're going to enforce a particular relationship between our vectors and the integrand.
Okay, so it's like setting up roadblocks along the integration highway and checking our vector's GPS at each one.
I like that analogy. Yeah, so the relationship that Levin's method enforces is this. F equals ATP plus ATP FF.
Okay, now that is a mouthful. Can we unpack that a little bit? What are all those symbols and what do they mean?
Sure, let's break it down piece by piece. So first, those angled brackets, AF, they denote the dot product,
Okay.
which is a way of combining two vectors.
Okay.
So SIP represents the dot product of our vectors P and W.
All right, so far so good. What about that prime symbol, the apostrophe?
That indicates a derivative, so ep(edge_w) is the derivative of the dot product of P and W with respect to x.
Okay, got it. And ATP, what's going on there?
So AT represents the transpose of the matrix A, which basically means flipping the matrix along its diagonal.
Okay.
And PA is the derivative of the vector P with respect to x.
All right, so we got derivatives, dot products, matrix transposes. This is a full-blown math party in here.
It's getting exciting, right?
It is. But what about that F on the right-hand side?
Ah, that's where our original integrand comes back into play. F is a vector that includes our smooth function, Fa.
Right, so we've come full circle, but how does this equation actually help us solve the integral?
Okay, so by enforcing this relationship at those strategically chosen collocation points, we end up with a system of linear equations.
Right.
It's like taking multiple snapshots of our vector and the integrand at those checkpoints and using those snapshots to build a solvable system.
So we've transformed a tricky integration problem into a more familiar linear algebra problem.
Exactly, and that's the brilliance of Levin's method. It provides this elegant workaround. It sidesteps those pesky oscillations and turns them into something we can handle efficiently.
Okay, I'm really starting to grasp the genius of this, but there's one thing I'm still curious about. You mentioned using Chebyshev polynomials in this process.
Right.
What role do they play?
Okay, so Chebyshev polynomials, they're a special type of mathematical function that's really well suited for approximating solutions, especially when you're dealing with oscillations.
Okay.
They're like a set of building blocks that we can use to construct an accurate representation of our vector would at those collocation points.
So they're like a high-fidelity blueprint for our oscillations.
That's a great way to think about it. They help ensure that our approximation stays accurate even when those oscillations get really wild.
I see. So Chebyshev polynomials are like our trusty allies in this mathematical battle against oscillation.
Exactly.
Okay, so it seems like we got all the pieces in place now. Levin's method transforms our integral into a differential equation. This clever equation connects that differential equation back to the integral, and Chebyshev polynomials help us approximate the solution accurately at those collocation points. It's like a well-choreographed dance, each step leading seamlessly to the next.
Beautifully put. And all of this is what allows pylevin to be so efficient and accurate. But remember, it's not just about the math itself, it's also about how it's implemented. And that's what we'll explore next, the clever implementation details that make pylevin such a powerful tool.
Okay, sounds good. I'm eager to see how they've translated all this beautiful math into a practical piece of software. Okay, so we've gone pretty deep into the theory behind pylevin.
Yeah, we've been through the mathematical trenches.
We've explored Levin's method, seen how it tackles those tricky Bessel integrals.
Right, we've laid the groundwork.
But now I'm ready for the main event, you know?
Yeah, let's see it in action.
Show me the results. How does pylevin actually perform in the real world compared to, other methods out there?
All right, so the paper does a great job of benchmarking pylevin,
Okay.
comparing it to a bunch of specialized tools designed for specific types of Bessel integrals.
Okay, so let's start with the basics. They tested it on the classic Hankel transformation, right?
Yeah, exactly. They used a package called Hankel, which, as you can probably guess, is all about Hankel transformations.
Right, so it's purpose-built.
Yeah.
So how did pylevin do against a tool that's specifically designed for that?
Well, it held its own remarkably well.
Oh, really?
Yeah, it achieved practically the same speed and accuracy as Hankel.
Wow, that's impressive.
Yeah, pretty good for a generalist going up against a specialist, right?
It is. It's like bringing a Swiss Army knife to a knife fight and coming out on top.
Exactly.
So let's up the ante a little bit.
Okay.
How did pylevin perform on a more complex problem, something from a field like cosmology, for instance?
All right, well, they tested it on calculating the galaxy power spectrum monopole,
Okay.
which involves integrating a function with a single Bessel function.
Right.
And they compared pylevin to Hankel,
Okay.
which is a package that uses FFT log,
Okay.
another powerful technique for Bessel integrals.
So another specialist, this time from the world of cosmology.
Yeah.
How did it fare against Hankel?
It was a close one. Hankel was slightly faster in this particular scenario.
Okay.
But pylevin was right on its tail, which shows it can compete even with algorithms that are specifically tuned for particular applications.
Right. So still a very strong contender.
Oh, absolutely.
Okay. So we've seen it go up against that Hankel transformation. We've seen it go up against, this galaxy power spectrum monopole calculation.
Right.
Did they push it any further? Did they test it against any other kind of FFT log based tools?
They did. They compared pylevin to pyleflog,
Okay.
which is a package specifically designed for FFT log transformations. And they used a particular test integral for this.
Right.
And once again, pylevin matched pythlog in both speed and accuracy.
Wow. So it really is like the Swiss Army knife of Bessel integration?
It really is. It's got a tool for every situation.
It does. But I'm sure they had one final boss battle in store for it, right?
Of course, they wanted to see how it would handle a really demanding task, calculating the angular power spectrum in the non-limber projection.
Okay. Now this is getting serious. The non-limber projection.
Yeah, this one involves not one, but two Bessel functions.
Oh, wow.
And they chose PyCCL as the opponent for this one.
Okay, PyCCL. So this is a new challenger.
Yeah, PyCCL is a highly optimized cosmology code.
Okay.
It uses a specialized FFT log implementation specifically designed for this calculation.
So they're really bringing out the big guns here.
They are. It's like bringing in a grandmaster chess player to challenge pylevin.
Okay, so this is the ultimate test.
It is.
A head-to-head between pylevin, this versatile newcomer, and PyCCL, the seasoned veteran.
The veteran, yeah.
How did it go?
Well, pylevin put up a valiant fight.
Okay.
So while PyCCL was faster,
Right.
due to its highly tuned nature, it's very specialized.
Right.
Pylevin still delivered remarkably accurate results.
So even when going up against this highly specialized, highly optimized code, it can still produce, comparable results.
You can, yeah.
That's impressive.
And it highlights a key point, while those specialized tools can be faster in specific scenarios,
Yeah.
pylevin's general approach allows it to perform well across a much wider range of problems.
So it's a bit like the tortoise and the hare again.
Yeah, I like that analogy.
PyCCL might be faster on a particular track, but pylevin can handle all sorts of different terrains.
Exactly. And there's another crucial aspect to consider.
Okay.
PyCCL's method relies on this assumption called separatability,
Right.
which means that the function you're integrating can be split into separate parts.
Okay.
But this assumption might not always be true,
Right. Yeah.
especially in some cosmological models.
Especially when things get a little bit weird and funky.
Exactly, and that's where pylevin has a real advantage,
Okay.
because its approach doesn't depend on this separability assumption.
So it's more flexible. It can adapt to those strange situations.
Exactly. It's ready for anything.
It is. All right. So we've talked a lot about pylevin's performance against these specialized tools.
Right.
But I think we've saved the best for last.
Yeah, the grand finale.
The real test of pylevin power lies in handling those integrals integrals involving multiple Bessel functions.
Oh, yeah, absolutely.
This is where it really shines, right?
This is where it really shows what it can do.
So how did it handle those multi-Bessel monsters?
They tested it on two integrals, one with two Bessel functions and another with three.
Okay.
And they compared it to the standard adaptive quadrature method.
Right.
And the results were amazing.
Okay, I'm on the edge of my seat.
Pylevin outperformed adaptive quadrature by orders of magnitude and speed, while achieving better accuracy and stability,
Okay.
particularly when those Bessel function arguments got really large.
So it sounds like pylevin is the undisputed champion when it comes to these multi-Bessel integrals.
It really does seem that way.
That's incredible.
And you know what? This ability to efficiently handle these complex integrals, it opens up a whole world of possibilities.
Yeah.
Especially in fields where they pop up all the time.
Cosmology, signal processing, optics, all those areas we talked about.
Absolutely.
Well, I'm truly impressed by pylevin. It's versatile, it's efficient, it's accurate. It sounds like a must-have tool for anyone working with these Bessel functions.
I would agree with that, yeah.
So as we wrap up this deep dive into pylevin, what's the one key takeaway you want our listeners to walk away with?
I think the key takeaway is that pylevin represents a significant leap forward in our ability to tackle complex mathematical problems that were once really difficult to solve. It's a testament to the power of creative thinking, finding new approaches, and developing tools that help us push the boundaries of scientific discovery.
Well said. It's been a real pleasure exploring the world of Bessel functions and the remarkable capabilities of pylevin.
Likewise.
And I'm sure our listeners are now eager to try it out for themselves and see what they can achieve with this powerful new tool.
I hope so, yeah. Go forth and integrate.
That's right. And who knows, maybe they'll be the ones to discover even more innovative applications for pylevin.
That's the beauty of it. There's always more to explore.
Absolutely. It's an ongoing journey of exploration and discovery, and tools like pylevin are the vehicles that propel us forward.
Yeah, they're the keys that unlock new doors.
So thanks for joining us on this deep dive into the fascinating world of Bessel integration. And until next time, keep exploring, keep questioning, and keep pushing the boundaries of what's possible.
Couldn't have said it better myself.
It's wild how Bessel functions just seem to pop up everywhere.
Oh, absolutely.
Like, you could find them describing anything from, the ripples in a pond after you throw a rock in,
right,
all the way to, modeling how strong a signal is in telecommunications.
Yeah. They really are kind of hidden.
Yeah, the unsung heroes.
Yeah, exactly, of a lot of science and engineering fields.
And, speaking of those unsung heroes, you actually sent us some stuff on calculating integrals that have Bessel functions in them,
right,
which I've heard to be a real pain.
Oh, they definitely can be.
So,
especially when you've got a bunch of Bessel functions all in the same integral.
Exactly. And that's where this paper on the pylevin package comes in.
Uh-huh.
Because they're claiming that they can actually handle integrals with up to 3 Bessel functions.
Wow.
And that's pretty impressive, right?
That is very impressive.
Yeah.
Most tools can only handle 1 or 2 at most.
Yeah. So being able to have 3 in there is a big step forward.
It's a huge step forward.
Yeah. And they're even benchmarking this pylevin against other software that's already out there.
Okay.
And the results look pretty promising.
That's really exciting.
Yeah, so before we really jump into how pylevin actually works, I think it might be helpful to just take a step back and remember why these integrals are such a challenge in the first place.
Right.
What is it about Bessel functions that make them such a headache to integrate using those kind of normal traditional methods?
Well, it all boils down to how much they oscillate. They're kind of all over the place. They go up and down as you change the input.
Okay.
And it's because they come from this particular type of differential equation that describes wave-like things.
Right.
So you get these characteristic oscillations.
Gotcha. So it's not an easy shape to just get the area under the curve.
Exactly. If you try to do it with a normal integration technique, you're going to need a ton of tiny little rectangles to get a decent answer, which just takes tons of computing power.
So it's like trying to nail down a wiggling worm.
Exactly. Those traditional methods just can't keep up.
They're not made for that.
No, they're not.
They're not made for that kind of complexity.
Which is why you need these fancy techniques, the one pylevin uses.
Right, to actually wrangle these oscillatory beasts.
Exactly.
Okay, so let's unpack how pylevin actually tackles this whole challenge.
Yeah.
The paper starts by going into the details of how it's implemented.
Mm-hmm.
So what stood out to you in that section?
Well, right away you can see how adaptable it is.
Okay.
It can deal with different orders of Bessel functions
Right.
and different arguments for them too,
Okay.
which means it can handle all kinds of problems.
Yeah. So it's not like a one-trick pony.
Exactly.
Yeah.
It's got a whole toolbox. It can handle all sorts of Bessel functions.
Like a multi-tool instead of just single screwdriver.
Exactly.
That versatility is
really nice.
really nice.
Oh, yeah.
And then they also talk a lot about how they've optimized it for speed and memory.
Oh, yeah. They've really thought that through.
Which I imagine is
absolutely
really important when you're dealing with these really intensive calculations.
Yeah. Especially for people like me who are always pushing the limits of what our computers can handle.
Right. Every little bit
helps.
of optimization.
It's a big difference.
It's a huge difference.
Yeah.
Okay, so it's adaptable, it's fast.
Yeah.
It's memory efficient.
And then there's this really cool trick they call ruse.
Oh, yeah. Tell me about that.
So it's designed to make things even faster.
Okay.
If you're doing the same kind of integral over and over.
Okay.
But with different functions.
Okay.
The idea is that some parts of the calculation only depend on the Bessel functions themselves, not the specific function you're integrating.
Okay.
So pylevin cleverly stores those pre-computed parts and reuses them, which saves a ton of time.
That's brilliant.
Isn't it?
Yeah.
It's like when you're baking a cake and you realize you can use the same frosting.
Yeah, for different flavors.
Exactly.
So you don't have to start from scratch.
You don't have to reinvent the wheel.
Every single time.
Yeah.
And I bet for someone like you who's running all these simulations.
Be a game changer.
Where all these similar calculations.
Seriously. In fields like cosmology, where we're constantly doing integrals with Bessel functions, this kind of optimization can save us weeks, maybe even months.
Wow. So we've got adaptability, speed, and this clever optimization.
Pretty good start.
Yeah, pylevin's off to a good start
here. It is.
Okay. But the paper also has this code example.
Yes.
To show you how to actually use the package.
Right.
Do you think it's worth going through? Even for,
I think so, yeah.
Our expert audience.
If you're familiar with the ideas, seeing an actual example can really help it click.
Yeah.
You know, like how it all comes together.
Excellent point.
Yeah.
So in this example, we see the user is defining the integral, right? They want to calculate. And it's got two Bessel functions of the first kind in there, multiplied by just a simple exponential function.
Okay.
They set the limits of integration.
Right.
And then they call pylevin's functions to do the integration.
It's almost like a recipe. You just follow the steps.
Right. It's very clear.
And it all connects back to the math. Like the code shows you how to specify the order and the arguments for the Bessel functions.
Right. Which is
key to pylevin's versatility.
Right. It's like
it's like the code is speaking math.
Yeah, exactly.
You can see the connection between the ideas.
It makes it easy to translate.
Yeah.
Yeah.
Between the abstract and the practical.
Right. And I like how the example also shows you how to use all the different features.
Exactly.
Like the roost trick we talked about.
Yeah, it's all right there.
So you can really take advantage of that for your own calculation.
It's really user-friendly.
Yeah.
You know, they give you the tools and the instructions so you can build whatever you need.
It's a good blueprint.
It is.
Follow.
It is. Yeah, it's like they made a whole programming language just for these Bessel function integrals. Yeah. You don't have to do all the low-level stuff yourself.
Right.
You just use their functions.
It's all about
let pylevin do the work.
Abstraction, making those complex things easier to deal with.
Exactly.
But I think the real test for anything new like this
absolutely.
is how it stacks up.
You got to compare it
against what's already out there.
Yeah.
And that's where this paper gets really interesting.
Okay.
Because they actually dedicate a whole section to comparing pylevin's performance with other software packages.
I like that.
It's like a mathematical showdown.
A showdown.
Versus the heavy hitters.
Yeah, who's going to win?
Right.
And they're not just using like random integrals.
Right.
They pick specific problems.
Right, practical problems.
That people actually use.
That researchers are actually dealing with.
Yeah, so it's not just theoretical.
It's real world stuff.
It's stuff that matters.
Okay, let's go to these comparisons one by one.
Sounds good.
First up is Hankel.
Okay.
Which is designed specifically for calculating Hankel transforms.
Right, Hankel transforms.
And for those who don't know, a Hankel transform is basically an integral with a Bessel function multiplied by another function.
Right.
And they pop up in all sorts of areas.
Oh, yeah.
Like signal processing.
Signal processing, image analysis.
Image analysis.
Yeah.
So they use Hankel to calculate this specific Hankel transform. And then they give the same problem to pylevin.
Okay.
And the results are pretty impressive.
Oh, really?
Pylevin is almost as fast as Hankel.
Wow.
Which is kind of amazing because Hankel's a specialized tool.
It's made for that.
It's built for that.
Yeah.
So for pylevin to be competed
To hold its own
with a specialist.
against a specialist?
Yeah.
That's impressive.
Is really impressive.
Yeah.
Yeah, it means that the underlying algorithms are super efficient,
They must be really good.
even when you're using them
Yeah.
for problems that pylevin wasn't
Right. Outside of its comfort zone.
specifically designed for.
That's a good sign.
Right.
Yeah.
Okay, next up,
Okay.
we've got Hankel.
Hankel.
Okay. Which uses this technique called FFT log.
Right. FFT log.
To calculate
Okay.
integrals with Bessel functions. And the test case here is
Okay.
calculating the monopole
Okay.
of the galaxy power spectrum.
Right. Right. Which is basically telling us
Yeah, tell us about that.
how much stuff is clustered together at different scales in the universe.
Right, so it's a key concept.
Oh, yeah. It's fundamental to cosmology.
Like cosmology.
Yeah.
And pylevin does just as well
Wow.
as Hankel
Really?
in this test.
Even though Hankel
Is designed for
this.
Yeah.
So again,
Pylevin's looking pretty good.
Pylevin's showing that versatility.
It is. It's
It
like
can compete
it's a decathlon athlete.
with specialists.
Yeah.
Yeah, I like that.
Excelling in all these different events.
Multidiscipline instead of just specializing in one.
Exactly.
Okay, we got 2 down, 3 to
Okay,
go.
bring on the next one. The next one is piflog,
Piflog.
which, as you might guess from the name,
Yeah.
also uses FFT log
Okay.
for these Bessel function integrals.
Right.
This time the test is an integral
Okay.
with a spherical Bessel function.
Okay, spherical Bessel function.
And again, pylevin shows similar speed
wow.
and accuracy
Unstoppable.
compared to piflog.
It is.
It's like this mathematical juggernaut.
Crushing the competition.
Right.
Yeah.
Crushing the competition.
One
Right.
integral at a time.
One integral at a time.
It's getting good.
Okay, but this next opponent
Okay.
might be a little tougher.
Okay, who is it?
It's PyCCL,
By CCL. Okay.
which is used a lot in cosmology for calculating the angular power spectrum.
Right, the angular power spectrum.
This involves an integral
Okay.
with 2 spherical Bessel functions,
Okay.
and PyCCL is built for this.
It's the specialist.
Yeah.
Okay.
And in this case,
Yeah.
PyCCL actually does win
Okay.
in terms of speed,
It's Pascal.
but there's a catch.
There's always a catch.
PyCCL relies on this assumption
Okay.
about the math of the function that you're integrating.
Right.
And this assumption
Yeah.
might not always be true,
Okay.
especially if you're dealing with
Like more complicated models.
more complex modules
Yeah.
or like modified gravity.
Right, where things get weird.
Yeah, so it's like PyCCL
It's
is
like a race car.
a specialized race car.
Yeah.
Super fast,
But only on a perfect track.
but only on that specific track. If you
Exact.
take it off-road,
Yeah.
it's not going to do so well.
It fall apart.
Whereas pylevin
Uh-huh.
might not be as fast in that one specific scenario,
Okay.
but it's more like an off-road vehicle.
It can handle anything.
It can handle
Yeah.
a wider range of
The rough terrain.
challenges. Yeah.
Yeah.
And that flexibility,
Yeah, that's
I
important.
imagine, is really important
Especially if you're exploring new stuff
when you don't know
where those assumptions might not hold.
what those assumptions are.
Yeah.
Okay, for the final showdown,
Okay, the Sertal box.
pylevin goes up against
Uh-huh.
just a general
Okay.
adaptive quadrature routine
Okay.
from this SciPy library.
Or SciPy.
So this is like a
Purpose.
generalist numerical integration method
Okay.
that's not built for Bessel functions at all.
So it's like
This is like bringing a knife
a knife to a gunfight.
to a gunfight.
Yeah.
And, as you might expect,
Yeah.
pylevin just dominates.
It wins big time.
It's not only like way faster,
Okay.
it's also much more accurate.
Wow. So it's both fast and accurate.
When the arguments of the Bessel function
Okay.
get large.
Right.
So it really shows you the power of using a specialized tool
You got to use the right tool for the job.
like pylevin
Yeah.
for these types of integrals.
That's enough.
A total knockout victory.
Pylevin takes the crown.
Right. It's defeated the specialist and the generalist.
It's the champion.
Okay.
Yeah.
So we've seen pylevin performs incredibly well
It does.
in these head-to-head matchups.
Yeah.
But for those who are
For the truly curious.
really curious,
Yeah.
the paper goes even deeper
Oh, really?
into the math behind all of this.
Okay. I'm intrigued.
Are you?
Let's get into the weeds.
To get into the weeds.
Yeah.
Okay, so buckle up.
Okay.
Because pylevin is based on this method
Uh-huh.
called Levin's method.
Levin's method.
And basically what this method does
Yeah.
is it transforms the problem of calculating
Uh-huh.
that oscillatory integral
Right.
into solving
Into solving.
a system of differential equations.
Differential equation.
No.
Okay.
You might be thinking,
I am thinking that sounds harder.
wait a minute,
Yeah.
differential equations.
Yeah.
Isn't that
More complicated.
even more complicated?
Yeah.
But it's actually kind of a clever move.
Okay.
Because differential equations, even though they sound intimidating,
Yeah.
they can actually be a lot easier to deal with numerically
Okay.
than those really wiggly integrals. It's like trading in a bucking bronco for a well-trained horse.
Okay, I can see that.
Yeah, you might think.
You think you're making it harder.
Why would I?
But you're actually making it easier.
Want to deal with a differential equation.
Right.
But the beauty of Levin's method is that it transforms it into something that's much easier to compute.
It's like taking a tangled mess of yarn and winding it into a neat little ball.
Right.
The yarn is still there.
Right.
But it's way easier to work with.
Right. It's organized.
Exactly. That's what Levin's method does.
It imposes order on that chaos.
Tames the chaos.
Okay, so how does it actually work?
Yeah, how do you actually do it?
The paper lays out all the mathematical details in the appendix. And it all starts with the integral.
Right, the integral.
That we're trying to solve.
Okay.
Which they write as h⁵
Okay, that looks a little intimidating.
I know, it looks a bit daunting.
Yeah.
But let's just break it down.
Okay.
Piece by piece.
Let's do it.
So that IF key, that just represents the integral itself.
Okay, the thing we're trying to find.
The thing we're trying to calculate.
Okay.
And then FE, that's the well-behaved part.
The good part.
Of the integrand.
The part that's not causing trouble.
Right, the part that's not oscillating like crazy.
Okay, gotcha.
And the curly braces around cot just mean that this function might depend on several parameters.
Okay, like KK and so on.
Exactly, like KK, etc.
Right.
And then the real troublemaker, as we've talked about.
The bad guy.
Is that WX.
Right, that's where the oscillations are.
Which represents the oscillatory part. Those are the Bessel functions.
Yeah.
That are giving us
headaches.
All the headaches and the ankle brackets. Those denote the inner product.
Right, the inner product.
Which is just a fancy way of saying we're combining two functions to get a single number.
Okay.
It's like taking two vectors and calculating their dot product.
Right.
You're basically measuring how much these two functions overlap.
Yeah, I get it.
And it's that interplay between the smooth function and the oscillatory one that makes the integral so hard to compute direction.
So we've got our integral set up.
Right.
Now, where does Levin's method come in?
Okay, so the key insight is to use a specific property of that oscillatory function.
Okay.
It turns out what is his reason would be satisfy it or much.
Okay.
A particular differential equation.
Okay.
Which they show in equation 9 of the paper, dwx fu fu. So here dwx dx. That just represents the derivative
how W changes.
Of W with respect to x.
Sx changes.
Right, essentially how W changes.
Yeah.
Sx varies.
Got it.
And the important thing is that this derivative is equal to the original function Wx.
Okay.
Multiplied by this matrix As.
Okay, a matrix.
And this kind of equation is called a first order linear differential equation.
Right.
And like I said before, it's got these nice mathematical properties that make it a lot easier to handle
than the integrals.
Than that original oscillatory integral.
So it's a good trade-off.
It is.
Yeah.
It's a brilliant move.
It is. You're taking this wild function and making it follow some rules.
Exactly.
You're taming it.
We're taming the oscillations.
I like it.
By forcing them to follow a rule.
Okay, so we've got this differential equation.
Yeah.
What do we do with it?
So now we can use another
trick.
Mathematical trick.
Okay.
The paper explains that if we can find a vector P.
A vector P.
That satisfies a certain condition.
Okay.
Then we can approximate that original integral.
Okay.
Using a much simpler expression.
Right. That sounds good.
And that condition is given by equation 10.
Okay.
SF SOP plus FA SF.
Oh, all right. That's another mouthful.
I know it looks even more intimidating.
Yeah.
But stay with me.
Okay, I'm here.
That prime symbol just means derivative.
Right, derivative.
And F is the transpose of the matrix A.
Right, transpose.
And F is basically the non-oscillatory part of the integrand.
Okay.
Just written a little differently.
Right.
But the important thing here is that this equation is setting up a relationship between PW and F.
Right.
And if we can find a P that satisfies this,
then we've got a shortcut.
We've got a shortcut.
To the integral.
To our integral.
Okay, but how do we find P?
So P is like the key.
The key?
That unlocks the treasure chest.
Okay.
Holding the solution.
I like it.
But how do we find it?
Right. Where is this key?
That's where Levin's method really shines.
Okay.
The idea is to break down P.
Break it down.
Into a sum of simpler functions.
Okay.
Called basis functions.
Basis functions.
And equation 13 shows this PMX is good. Okay,
Uh-huh.
so those are the basis functions.
Okay.
And the CM are are coefficients
Coefficients.
that tell us how much
Okay.
of each basis function we need.
Like a recipe?
Yeah, it's like building a house
Okay.
out of Legos.
I like that.
The basis functions are the individual Legos,
Okay.
and the coefficients tell us
How many of each?
how many of each brick we need to
Gotcha.
build the final structure.
And just like with Legos.
Yeah.
You got to pick the right ones.
You got to pick the right one
For a stable house.
for a stable structure.
Yeah.
And pylevin uses these things
Okay.
called Chebyshev polynomial
Chebyshev polynomials.
as their basis functions.
Okay.
And these polynomials have really nice properties
Okay.
that make them really good
Good for
approximating functions,
approximating functions. Yeah.
especially the ones that oscillate.
The oscillatory ones.
Okay.
So they've picked
They've chosen
one
both.
Legos for the job.
Yeah.
Okay. Now, once we have
Okay.
this decomposition of px,
Yeah.
we can plug it back into that equation
Okay.
we had before
Yeah.
and do some mathematical magic.
Some math.
And this leads us to equation 14,
Okay.
which is like the heart
The heart of it.
of Levin's method.
Okay, what is it?
It was actually a system
14.
plus 18.
Okay, it's a lot of symbols.
It is a lot of symbols.
But what does it mean?
It's actually a system,
Of linear equations
okay?
that we can solve
We can solve it.
for those unknown coefficients.
Oh, right, the CM.
The CMs.
Okay.
And once we have them,
Yeah.
we can plug them back in
Plug them back
to
in.
the equation for PS
Okay.
and use that to approximate the original integral.
The integral, we did it. We did it.
We solved
We
it.
solved the puzzle.
We solved the puzzle.
We found all the pieces.
So we've transformed this problem
Yeah.
of calculating this
It's
complex
this crazy interval.
oscillatory integral
Yeah.
into just solving the system of linear equations,
That's amazing.
which is much more manageable.
Math is so powerful.
It really is.
Yeah.
And the paper actually gives specific examples
Okay.
of how to apply Levin's method
Uh-huh.
to integrals
Okay.
with 1, 2, or 3
Wow.
spherical Bessel functions.
So it covers all the bases?
It does.
Okay.
And the details get
They get a little messy.
a little messy.
Yeah.
But the general idea
The idea is the same.
is the same.
You transform the integral.
Transform the integral.
Find P.
Right.
And approximate the integral.
And you do to go.
It's like a master key.
It's
There's all these Bessel function integrals.
Yeah, and what's really cool is that Levin's method
Uh-huh.
isn't just limited
No.
to Bessel functions.
Really?
You can actually use it.
You can use it for
Other kinds of oscillatory functions
other oscillations. Wow.
as well.
That's really powerful.
The paper even hints at that
Okay.
in the appendix.
Yeah.
Basically saying as long as you can express those oscillatory functions
Okay.
in terms of a recurrence relation,
Recurrence relation.
which is just a mathematical relationship
Okay.
that links successive terms,
Right.
you can adapt Levin's method
to handle them.
That's
some fun.
So pylevin,
Yeah.
which is already a really powerful tool,
Yeah.
has the potential
To be even better.
to become even more versatile
Yeah.
in the future.
It could handle a whole new class of problems.
Right. It could be expanded
It's exciting
to all sorts
of to think about the possibilities.
oscillatory problems.
Yeah.
So this deep dive
Yeah.
has really shown us
It's shown us
the power of these specialized tools and clever algorithms for dealing with
this complex math problem.
mathematical challenges.
Absolutely.
And for someone like you,
Yeah.
who's doing all these simulations
Yeah.
and data analysis,
Pylevin could be a game changer.
I think so
The
too.
speed, the accuracy,
Yeah.
the fact that it can handle multiple Bessel functions.
Yeah.
It's a big deal.
And the potential for
yeah.
even more in the future.
It's a really exciting development.
Well, I think we've really explored
I think so.
the depths of this paper
We went deep.
on pylevin.
We did.
And if any of our listeners are
Yeah.
as intrigued as we are
If you're curious.
by this new tool,
Yeah.
I encourage you to check out
Check it
the
out.
pylevin package
Yeah.
and the documentation.
See what it can do.
You might just find that it unlocks
It might unlock
new possibilities in your own work.
Yeah.
And makes those tricky Bessel function integrals
A little less scary.
a little less daunting.
Yeah.
Until next time, keep diving deep.
Yeah.
So ever hit a wall trying to numerically integrate Bessel functions? You know those things that pop up all over physics problems with rotational symmetry?
Oh, yeah. It's a real pain.
It's like using the wrong tool for the job.
Standard numerical integration methods like quadrature, they just can't handle those rapid oscillations you get with Bessel functions.
Right. And the complexity just explodes when you have multiple Bessel functions multiplied together in the integral. Your computation time goes through the roof.
Exactly. And that's where this Python package called pylevin comes in, I think.
Pylevin.
It's designed to handle those tricky Bessel function integrals.
Ah, okay. Efficiently and accurately, I see.
From what I understand, it uses something called Levin's method.
Yeah, that's right. Instead of trying to directly tackle those oscillations, Levin's method kind of sidesteps the problem.
Oh, how's that?
It transforms the whole integration problem into solving a system of differential equations.
Clever. Differential equations can be much more manageable computationally.
Okay, so before we get into the weeds of Levin's method and pylevin, let's take a step back. Remind ourselves why these Bessel functions are such a headache.
Sounds good.
What are they, and why do they always seem to show up in problems with rotational symmetry?
So Bessel functions are solutions to a specific type of differential equation, the Bessel equation.
Okay?
And this equation, it naturally arises when you're dealing with systems that have, well, circular or cylindrical symmetry.
So anything that spins, vibrates in a circular pattern, or has a cylindrical shape.
You're going to run into Bessel functions. They'll be lurking in your equations.
Got it. And it sounds like the real challenge comes when you need to integrate these functions numerically.
Especially when you have multiple Bessel functions multiplied together.
Right, because then those oscillations, they start interfering with each other, creating this really complex pattern.
And traditional integration methods just can't handle that accurately.
Or efficiently. So if I'm hearing you right, this pylevin could be a game changer for researchers who have to work with Bessel functions all the time.
Oh, absolutely. The hope is to make these calculations that used to be almost impossible. Not only possible, but also, fast.
And the developers have really tried to make it user-friendly too, from what I've seen.
Yeah, they have. It seems pretty straightforward to use.
Let's dig a little deeper into Levin's method before we look at pylevin.
Okay.
Turning an integral into a differential equation. It seems a little like magic to me.
It's clever, for sure.
How does that even work, conceptually?
Well, the key is that even though these Bessel functions oscillate so rapidly, they still follow a pretty predictable pattern.
Ah, okay. So instead of trying to brute force our way through each wiggle of the Bessel function,
Exactly.
Levin's method finds a way to describe the overall behavior, the underlying structure of the oscillations.
Right. You construct a differential equation that captures how those oscillations change and evolve over time.
Ah, I'm starting to see it. We're finding a smoother way to describe this jagged, complex thing.
I like that analogy.
And once we have that differential equation, we can use standard numerical methods to solve it, right?
Yep. Much more efficiently and accurately. It's a much smoother ride computationally.
It's like finding the hidden rhythm of a complex piece of music.
Mm-hmm.
Once you understand the beat, the underlying pattern, it's much easier to follow along.
That's a great way to put it.
But I have to ask, how did anyone even think to apply differential equations to this kind of problem? The connection seems so unexpected.
It really does, but that's often how the most elegant mathematical solutions come about, right? Someone finds this surprising link between two seemingly unrelated areas of math.
And suddenly a whole new set of tools become available.
Precisely. In this case, it's using the tools of change, these differential equations, to understand these special functions and their crazy oscillations.
It reminds us there are always more connections to be found, waiting to be uncovered. Now, I know there are already some tools out there for dealing with Bessel function integrals.
Right.
What makes pylevin stand out? What's different about it?
So a lot of the existing tools are very specialized. They might work really well for integrals with one or two Bessel functions,
Okay.
but they're not flexible enough to handle a wider range of problems. Pylevin, though, it can handle integrals with up to 3 Bessel functions.
Oh, wow. Of any order, right?
Yeah, of any order and with any arguments. It's a much more versatile tool.
So it's like it's like the Swiss Army knife of Bessel function integrators.
Exactly. It can adapt to so many different situations, and it can be used in many different fields, too.
That's really impressive. But does this versatility come at a price? Is it slower than those more specialized tools?
Well, the developers did some serious benchmarking. They compared pylevin's performance head-to-head against these existing codes.
And how did it do?
For integrals with just one Bessel function, pylevin performs about the same as established tools like FFT-log, sometimes a tiny bit faster, sometimes a tiny bit slower. But when you have 2 or 3 Bessel functions, that's where pylevin really shine. It just blows the competition out of the water.
How much faster?
We're talking speed improvements of up to 4 orders of magnitude.
4 orders of magnitude. Compared to what?
Compared to the traditional quadrature methods.
Wow. That's incredible. That's like going from walking to teleporting.
It's a huge difference.
And it's not just about speed, is it? It has to be accurate, too.
Oh, yeah, definitely. And it is. It achieves that speed while still maintaining excellent accuracy.
So pylevin's fast and reliable. Amazing.
It's all thanks to that clever implementation of Levin's method.
So they didn't just use Levin's method straight out of the box, did they?
No, they didn't. They used an adaptive version, so pylevin can adjust its calculations as it goes along.
Interesting. Like it learns as it works?
Kind of. It refines its approach based on the integrand and the desired level of accuracy.
That's smart.
It's like having a GPS that reroutes you based on traffic. You get to your destination much quicker and more efficiently.
Okay, that makes sense. I'm really curious to see how they implemented this.
Me too.
But before we dive into the nuts and bolts of pylevin,
Yeah.
let's talk about the testing they did. Did they just make up some Bessel function integrals?
No, they actually tested it on real problems.
Like problems researchers actually encounter?
Exactly, in fields like cosmology and signal processing.
Ah, okay, so they put it through like paces. What kind of examples did they use?
One example was calculating Hankel transformations.
Hankel transformations.
They're really important in signal processing for analyzing signals and manipulating them.
So for engineers working on things like audio processing or image compression,
Exactly.
pylevin could be a game changer.
It could really speed up those calculations, which would allow for more complex algorithms.
Did they use any other real-world examples?
Yeah, they did. They also tackled a problem from cosmology, calculating the monopole of the galaxy power spectrum.
The monopole of the galaxy power spectrum.
It's a way of analyzing the distribution of galaxies in the universe.
Ah, I see. And I imagine that could be pretty computationally intensive.
It is. It involves huge data sets.
So pylevin could help make those data sets a bit less daunting for astronomers.
Exactly.
It sounds like they really tested it thoroughly. They showed that it can handle real-world problems, and efficiently, too.
They did. They even used it to calculate the non-limber projection for the angular power spectrum.
Another cosmology thing. They covered a lot of ground. This pylevin package sounds incredibly promising.
It does, doesn't it?
It really does. It opens up so many possibilities for research.
Especially in fields where Bessel functions are, everywhere you look.
Okay, well, now I'm even more eager to see how they implemented all of this. Let's get into the nuts and bolts of pylevin. Let's see how it actually works.
All right, let's do it.
Okay, so let's imagine we want to actually use pylevin to solve one of these Bessel function integrals. What would be the first step?
The first step is to define the non-oscillatory part of what you're trying to integrate, the integrand.
Okay.
That's the part of the function that behaves nicely. The part that doesn't have all the crazy rapid oscillations.
Ah, okay, so we're kind of separating out the good from the bad.
Yeah, exactly. We isolate the source of all the trouble, those oscillations, and then we can let pylevin deal with it using Levin's method.
Makes sense. What's the next step?
Next, you need to specify the integration range.
Oh, yeah.
So that's the interval over which you actually want to do the calculation.
Just the start and end points of the integral.
Right. And then you have to tell pylevin about the Bessel functions themselves.
Oh, right, of course.
What type are they?
Are they spherical?
Spherical Bessel functions often show up in problems that have spherical symmetry.
Uh-huh.
Or are they cylindrical Bessel functions, which are more common when you have cylindrical symmetry?
Got it.
You have to specify that.
And we also need to tell it the order of the Bessel functions, don't we?
Absolutely. The order will determine the specific shape of those oscillations.
Okay. And I guess we also need to specify how many Bessel functions are actually involved in the integral.
Exactly. Whether it's 1, 2, or 3, pylevin can handle it.
So to recap, we define that non-oscillatory part. We set the integration limits. We specify the types and orders of the Bessel functions. And then are we done? Can we just hit go and let it run?
Almost. You do have some control over the calculation process. You can change some of the settings.
Oh, good.
Like you can configure how many collocation points pylevin will use.
Collocation points. Remind me what those are.
There's specific points without that integration range where pylevin will actually evaluate the integrand. It's kind of like having these sensors placed at strategic points.
Okay.
They capture how the function is behaving.
So if we don't use enough of these collocation points, we might miss some details, right?
Yeah, you could miss out on some of the important details of the function's oscillations.
Like trying to understand a song from hearing just a few notes here and there.
Exactly.
You might get the general idea, but you'll miss the nuances.
And of course, if you use too many collocation points, the calculations get really slow.
Right. It's all about finding that balance. But luckily, pylevin uses that adaptive version of Levin's method, right?
It does.
So it should be able to find the sweet spot.
Pylevin will adjust the number of those collocation points as it goes along, depending on the accuracy you need and how complex the integrand is.
Okay. That's very cool. Are there any other settings we can play with?
You can also specify the desired level of accuracy for the whole calculation, so you're telling pylevin how hard it needs to work.
Ah, okay.
How much effort it should put into refining that solution.
So if I need a really, really precise result, I can just crank up that accuracy setting, right?
Yeah, exactly. But keep in mind, if you go for super high accuracy, it's probably going to take longer to compute.
Yeah, makes sense. It sounds like pylevin gives the user quite a bit of control.
It does. And there's one more really cool feature. You can reuse some of the quantities that pylevin has already calculated.
Oh, what do you mean?
Let's say you're doing some kind of simulation.
Okay.
And it involves doing a bunch of Bessel function integrals that are pretty similar. Maybe they have slightly different parameters or slightly different integration ranges.
Right.
Well, instead of starting from scratch each time,
Yeah.
pylevin lets you just reuse those calculations from the previous runs.
That's really smart.
It can save you a ton of time.
Especially if you have to do a lot of these integrals. It's like meal prepping, but for Bessel functions.
I like that.
So pylevin remembers what it's already done and only recomputes what's absolutely necessary.
Yeah, exactly. And this is especially valuable in a field like cosmology.
Why cosmology specifically?
Because researchers in that field often have to run these large-scale simulations.
Oh, okay.
And those involve, you guessed it, tons of Bessel function integrals.
So this feature could be a real time saver.
It could be huge.
It sounds like the people who made pylevin really thought about the needs of people who work with these types of problems.
They did. It's a very powerful package, but it's also super user-friendly.
That's great.
To really appreciate how all of this comes together, we should probably look at some actual code.
Oh yeah, I was just thinking that.
Would you like to see how pylevin is used in practice?
Absolutely. Let's see this thing in action. All right, I'm ready for some code. Show me how you would set up a simple Bessel function integral and solve it using pylevin.
Okay, sure. Let's start with a really basic example. How about one with a single spherical Bessel function?
Sounds good.
Let's say we want to calculate the integral of x2 j1rx
Okay.
from 0 to 5, where j1 on x is the spherical Bessel function of the first order.
So the non-oscillatory part is x2, and we're integrating from 0 to 5. Got it.
Right, so here's how you do this in pylevin. First, you import the necessary modules.
Which are?
You'll need numpy, obviously, for numerical calculations.
Mm-hmm.
And you need to import spherical Bessel transform from the pylevin package.
Okay, so it's python.import nummy as np from pylevin import spherical Bessel transform.
Yeah, exactly. What's next?
Well, we need to define the non-oscillatory part of our integrand, right, as a Python function.
Right, which would look like this. Python,
Return x2.
nice and simple. Okay, so now what?
Now we need to create a spherical Bessel transform object.
Okay.
We have to tell it the order of the Bessel function, which is 1 in our case, and the integration range.
Right, so the code looks like python.transform equals spherical Bessel transform x min AO 0 x max over 5.
Perfect.
So nu represents the order. What if we were using a cylindrical Bessel function instead of a spherical one?
Pylevin has a separate class for that, cylindrical Bessel transform, but the way you use it is very similar.
Okay, that makes sense. So we have our transform object set up. Now, how do we actually perform the integration?
Easy. You just call the transform method.
Okay.
You pass it your non-oscillatory function f, and then you also specify what accuracy level you want.
So Python result equals transform f rtol 1e6.
Exactly.
Rtol sets the relative tolerance.
Right.
And that determines how accurate the result will be. And then that's it. The variable result now holds the value of the integral.
That's it. Pylevin handles the rest, all that complexity of Levin's method, dealing with those oscillations, and it's all happening behind the scenes.
This code is so clean and simple, it's pretty amazing considering everything that's going on underneath.
It is, and it gets even better. Let's say you want to calculate the same integral, but with a different upper limit. Instead of going from 0 to 5, let's go from 0 to 10.
Okay.
Would we have to create a whole new spherical Bessel transform object?
I don't know. Would we?
We wouldn't. Pylevin lets you reuse those quantities as already computed, so you can calculate these integrals with different parameters without having to start from scratch every time.
Show me, show me.
Okay, so instead of making a new object, we can just update the xmax attribute of our existing transform object, and then just call the transform method again.
Ah, I see.
Like this, python.transform.xmax equals 10, new result equals transform f rtol 1e6.
So pylevin just remembers what it's already done and only recalculates what's absolutely necessary?
Yep.
That's super efficient.
It is. It can save so much time, especially if you're doing a lot of these integrals.
Okay, this is really impressive. The pylevin developers have thought of everything.
They have. They really wanted to make this whole process of working with these Bessel function integrals as easy as possible.
Now I'm curious, does Levin's method have any limitations? Are there cases where it might not work so well?
That's a good question. So Levin's method is really effective for these oscillatory integrals, like the ones with Bessel functions, but it does have some limitations.
Like what?
The main thing is that the non-oscillatory part of your integrand, it needs to be smooth. It can't have any sudden jumps or discontinuities.
Ah, so it needs to be well behaved.
Yeah.
Not too wild.
Right. If that non-oscillatory part is too rough, then Levin's method might not accurately capture what's going on.
Oh, okay, I see.
It's kind of like trying to fit a smooth curve to a bunch of data points that are just all over the place.
Ah, okay.
It doesn't really work.
What about the Bessel functions themselves? Are there any limitations on what types of Bessel functions or what orders of Bessel functions Levin's method can handle?
So in theory, Levin's method can handle Bessel functions of any order. But the more complicated those Bessel functions get, the harder the calculations become.
Right.
As the order of the Bessel function gets higher, the computations can get pretty slow.
Even with Levin's method.
Yeah. But in most real-world situations, Levin's method, especially how it's implemented in pylevin, is super efficient.
Well, we've covered a lot today. Bessel functions, the challenges of integrating them.
Levin's method.
Levin's method, right. And this amazing pylevin package. It seems like this tool could really change things for researchers in all kinds of fields.
I think so too. It's a great example of how powerful specialized tools can be.
And it shows that even tools that seem really specialized, like pylevin, they can have a huge impact. They can open up whole new areas of research.
Absolutely.
So to all our listeners out there, we hope you enjoyed this deep dive into the world of Bessel functions and Levin's method. And if you work with these kinds of integrals, definitely check out pylevin.
It's a really cool package. It could save you a lot of time and headaches.
Until next time, keep exploring and keep learning.